Connected intelligence. I'm not going to talk much about the connectivity part. I'm going to talk about the intelligence part. And in particular, I'm sort of going to go back to basics. I'm not going to talk about XMOS, although I'm employed by that company. But you can infer what you like from what I say as to what we might do in the future. I couldn't resist this picture. This is a picture from the film I, Robot. You've probably all seen it. We're not going to do that. Well, not yet. So we are at a point as an industry of great discontinuity, certainly the greatest that has occurred in my short career. There are three things that have sort of come together, some of which have already been discussed. First of all, an abrupt end to Dennard scaling caused by power limits in silicon, and in the digital world, not likely to be solved by any technology currently on the radar, not likely to be solved by 3D packaging, for example, because it's a power density problem. And you've probably seen this graph, some of you, which shows the advance of CPU clock rates over time. And it hit a brick wall in 2005, 90 nanometers, roughly. It's not going any further. And the industry's reaction to that has been, we now just build more microprocessor cores, on one chip. Ubiquitous parallel processing. We've been toying with the idea of parallel processing as an industry for years. Now we have no choice. We have to do it. So that's the first shift. The second shift, Wally's already talked about a lot, whether it will continue or not. I hope Wally got across the message that if you believe it will continue, you have to believe in some new technology appearing. Personally, I can't see one in the near future, so I think for now, it's stopping. This, fortunately, gives us a renewed imperative. I say fortunately from my point of view as a chip designer, a renewed imperative for efficiency. We have to choose the right solution for the application problems we have. Should mean that Wally and his friends sell more expensive EDA tools too. And the third fundamental shift, and I think this is the biggie for me, is a shift in the type of applications that we would now like to apply our computing technology to. And this is a shift to genuine intelligence. I don't mean smart in the sense that marketing people use smart. Your smartphone is not smart. Your smartphone does not attempt any intelligence process. However, it can connect to the cloud, which increasingly does allow for intelligence. I'll talk a bit about that as we go forward. First of all, how do we define intelligence? There is no accepted standard definition, even amongst psychologists, never mind computer scientists. But practically speaking, we could say that intelligence is required where one of these three things is true, or maybe more than one. Where, for example, a problem is formally intractable to algorithms. We can mathematically prove that there is no algorithm faster or more effective than exhaustive search, and exhaustive search is usually too expensive. Almost everything a designer does, whether a designer of chips or a designer of aeroplanes, turns out to be NP hard. In chips, all of the EDA tasks like placement of objects on a die or routing of objects together are NP hard. Obviously, we've learned to solve them pragmatically and heuristically. But we need intelligence to do that, which is why humans are in the loop. The second characteristic is problems for which we simply can't conceive of an algorithm. So recognize your mother is the classic example. We can all do it. None of us can write a computer program to do it. We can, however, write a computer program and train that program to do it. That's an intelligent program. And the third case is where there's not enough input information for an algorithm to be able to deductively produce a result. And the classic example here is computer vision. Vision relies on a number of 2D views of a 3D world, and from that it must infer the 3D world. Well, that's impossible, because there's less information in those 2D pictures than there is in the 3D world. You and I can do it, however, can't we? How do we do it? Because we are intelligent. We have built in our minds, using our experience, a 3D model of the way the world usually works. And when we see 2D images of it, we convolve those or compare those with our 3D model, and that allows us to establish a belief in what the 3D world really looks like. So intelligent machines augment programs with models. Now this is massive. These models have to be learned. They're not programmed. So software, as we know it, is going to develop a whole new leg. As well as programmers, there will be trainers or teachers or something that causes learning to occur. The second thing is results are probabilistic because these things are intractable, therefore there is no certainty. The best we can hope for is a reasonably good guess. And then we need decision policies to decide what to do with that uncertainty. And intelligent machines, because there is no certainty with non-determinism, may correctly compute incorrect answers, just like people. So we've heard about security as being a concern going forward. Well, how about this? This is not really security. This is failure of judgment. So if we look at the process of intelligence, graphically, here's a little picture. So we have some sensors producing some information. The first thing we need to do with the information is learn from it to produce a model of correlations between the different things that we've sensed. And then once we've got a model, we can take further sensory input and use a process of inference to produce a probability distribution over the possible things that might be correct, a distribution over truth. And then a decision policy takes that uncertain distribution and decides what to do. So a machine that does this lot is an intelligent machine. And the nice thing is that these difficult processes of learning and inference, and to some extent policy, are starting to yield to algorithms. We are starting to understand them at a fundamental mathematical level. And they work, actually. And therefore, we can now build a machine that's intelligent for the first time. This is something that's maybe occurred in the last decade. And at the moment, it's most prevalent in the cloud, actually, in advertising machines. They still need to acquire intelligence, though. We haven't actually made the thing intelligent. We've given it the capacity for intelligence, the capacity to learn a model. And today, intelligence, most prevalent in the cloud. In future, it will be everywhere. It will be embedded everywhere. Every moving machine will need intelligence. We'll need every moving machine to perceive the world as we see it. Application examples, machine vision, the ability to identify objects and track them. Car driver assistance systems, identifying people, identifying bicycles, other cars, like road signs, white lines. Robot navigation, the ability of a robot to work out what the shape of its environment is and where it sits in that environment, and to plan what it does next on the basis of those inputs, requires intelligence. It's not something you can do without intelligence. Adaptive control, particularly high degree of freedom control. We've spent many, many years, or the research community has spent many, many years trying to make robots walk. It turns out that a multi-segmented inverted pendulum, i.e. a pair of legs, is quite complicated. It's so complicated, in fact, that that form of control theory is called chaos. It's not actually intractable. It's just so complicated we can't work out how to do it. And the most successful control strategies applied so far to controlling that sort of complex, multi-segmented, high degree of freedom machine turn out to be ones where we haven't solved the problem. We've simply built a learning machine and trained it to be able to balance. And a typical robot can have 6 degrees of freedom for each joint. I've got, I don't know, a couple of dozen joints. I've got a lot of degrees of freedom. So trying to build my model of how I work, my dynamics and my kinematics, is a problem of doing optimization in maybe a couple of 100 dimensions. It's quite a complicated mathematical problem, but it's not intractable. The extraction of information, as opposed to raw data, from sensors, for example. MPEG compression behind a camera is not intelligent. We might call that camera a smart camera, but it's not smart at all. It's not actually added anything to our knowledge of what was in the image. It's just squeezed it down a fewer bits in a pipe. However, if the camera were to tell us there is an intruder, 6-foot-high male, moving across the patio, then that would be intelligent. And how would it do that? By building a model of what intruders look like, and what cats look like, and other things in that space. And then finally, dialogue interfaces speech conversations with machinery. I've got an example, so I'll talk about that. In fact, I've got 3 quick examples I'll show you. So the first one is, well, a typical application might be a vacuum cleaner, but any sort of robot moving in an environment. One of the big challenges of robotics is a thing called simultaneous location and mapping, SLAM. And there was a massive breakthrough in SLAM about 8 years ago when researchers first started treating it as a probabilistic inference problem. It's a chicken and egg problem. The task is, that, so the robot's just had its eyes opened in an alien environment. It needs to work out what the environment looks like and where it is in the environment. So it wants to draw a map and position itself in a map. If it knew where it was, it could use its sensors to draw a map. If it had a map, it could use its sensors to work out where it was. So chicken and egg. The sensors are unreliable. Its own sensors are unreliable, and its actuators are inaccurate as well. And also landmarks that it might choose. It doesn't know anything about its environment, so it might just choose an edge, which could be a wall edge or a door or a picture on the wall or something like that. But it might choose something like that as a landmark, and then it might try moving a bit and see what happens. And then from that, it could deduce something about the environment it was in. But these things might move, and all of the information it has, odometers on its wheels, for example, its wheels might slip, it might be on a carpet. They can be unreliable. So its knowledge, even as it gains knowledge as it moves about, is probabilistic. And it has to accept that some of the information it's got might be wrong. But this problem now is tractable. We can build machines, robot machines, which to reasonable accuracy, say the accuracy required of a vacuum cleaner, could wander about your house, never having seen your house before, and could adapt to the fact that you move the furniture or the dog gets in the way. And the reason why this is interesting is because it's one of those things that's really simple for us to do and yet really complicated for a machine to do. We've only just cracked it, but now we've cracked it, we can deploy it widely. The amount of compute it requires is uneconomic today, which is great because it gives us all an opportunity for a new business. And we have a sort of a sales proof that you can sell semi-intelligent vacuum cleaners in very large quantities, even to early adopters. So this thing, there's over 10 million of these have been sold. They cost about 500 quid, and they're not intelligent. This is like one of those child's toys. It wanders around, kind of bumps into things. Has a little bit of intelligence. It tries to work out how far away things are before it bumps into them too hard. But you will find it executes a very random walk over your living room. It will clean certain parts of your floor 10 times and rarely visit others. But we can improve that. So there's an opportunity. It's a multi-billion-dollar opportunity before we've put intelligence in. And of course, the self-driving car will require the same DSLAM solutions. Second example, speech dialogue interface. This is what I want to be able to do. I want to be able to talk to my car, particularly when I've got my hands on the wheel and I'm concentrating on driving. I don't want to have to fiddle with buttons down here to change the temperature. I just want to say, Jenkins, temperature up, please. Now, speech recognition is a done deal, actually, pretty much. I mean, you can talk to your phone, talk to Siri, or talk to EV on your Android system, or what's the new Microsoft thing called Cortana, I think, came out this week. And it will reproduce on your phone the sentence that you have said. So that's fine. It can do all the signal processing, and then it can correlate that with words and correlate words into grammatical structures. It's got a model of English grammar, and it will reproduce sentences. Great. Trouble is, it doesn't understand you. You've probably tried Siri. Sometimes it does, but most of the time it doesn't understand you. When you ask Siri to do some work, typically it uses 300 server-class CPUs to try and understand you, and then fails. And the problem is that human speech is pretty poor as a carrier of information about what you mean. Now, if you had a dialogue state diagram, for example, and you could try and work out how you are moving the conversation, or how the conversation is moving through that state diagram, again, probabilistically, because you're never going to be certain, then you could try, for example, to track the information content of a conversation, and that's what you and I do in our brains, and then you wouldn't need to extract all the information from the spoken words sort of as they're delivered. That's very hard if you want to talk about philosophy or politics. But in a car, for example, where the dialogue space concerns only the climate and the infotainment system, it's not that hard. There are only so many things you can be talking about. So if I can reduce the dialogue state space, I've massively simplified my problem. And the second game changer is if I can do it fast enough that I can have a natural speed interaction with my car, then the car can ask me clarifying questions and make suggestions. And that very rapidly converges understanding of meaning as opposed to simply recognizing spoken word. This is almost there. We can almost do this. We can do it for very small state spaces. There's a trial in Cambridge where you can ring up a phone number and ask for restaurant recommendations. And you can ask for Italian or Chinese or Japanese restaurants, and you can say, I'm in this street or that part of town, and it will try to work out what you're saying, and it will ask you clarifying questions. Very, very small state space, again, requires server cluster compute today, but I can tell you that server cluster compute is operating on a job for which it has a spectacularly low efficiency. So if we were to build better machines for the job, then we could do it on something that was economic enough to go in your car. Final example, Kinect. You've probably all seen this. Terrific example of the mass deployment of machine learning, real learning. So this one is interesting because it doesn't learn online. All the learning is done offline, and then it just does the inference. Its function is to track human skeleton poses in real time. It projects a speckle pattern of laser light at you. You can't see it, it's infrared. And then it looks at, through a camera, infrared camera, it looks at the distortion of the speckle patterns, and it can get from that a 3D image. So it gets a 2D view with 3D depth information. And what it does is having spotted what the 3D depth map is, it then uses an inference process to correlate that with a 25-joint skeleton model. Each joint has 6 degrees of freedom, so 25 times 6 dimensional optimization space. It was trained by Microsoft on 1 million training poses, and it took 24,000 CPU hours for each training run. So in fact, they did it on a cluster of 1,000 CPUs, 24 hours each time they did it. But the point is, that's all offline. The actual inference itself can be done with 15% of the processing power of the Xbox chipset, which is about as much as a mid-class ARM. So we need some more machines. We need some new machines. And this is the reason why. These new computation patterns are characterized by some very different things to the things that CPUs and GPUs were designed to do. The data structures are large, irregular, and sparse. These high-dimensional data structures I've alluded to earlier. And that means that vector machines don't help at all. In fact, they get in the way. And unfortunately, that has been our approach to trying to improve the amount of compute we have available, is to produce vector machines. Most of them are GPUs, but vector machines in CPUs as well. The second thing is, there is huge aggregate compute, and there's huge available parallelism. That's pretty handy, because we've got to use parallelism now, so there should be a natural fit post-Denard. There is very little compute per communicated bit. That's unfortunate, because GPUs are built assuming the opposite. And there is no data access locality, so caches are actually harmful. That's a really big statement to a CPU designer, because as one, I can vouch that about half of the effort that's ever gone into CPU design has gone into the caches. Now they're useless for this. In fact, they're worse than useless. They get in the way. And today, the most powerful chips we produce are the GPUs. And what they do is that they take a 3D world model and they produce 2D views of it. That's an entirely deterministic algorithmic process. There's no intelligence required. What we'd like to do now is vision, which is the opposite. This is an inference process. It is much, much harder than that. And we're not going to produce chips that are 1,000 times bigger than that one, so we'd better produce chips that are more efficient at it. Is there scope? Yes. This shows dense matrix multipliers and sparse matrix multipliers. You can interpret that as GPU-friendly stuff, the new stuff. And this is trying to run it on a single CPU. Actually, if you run it on a GPU, you get a bigger difference. But this shows that the efficiency of CPUs drops by 1,000 times with this workload. The message here is we need to build something different, something that will get that 1,000 times back. Then that massive compute workload to do your dialogue system to allow you to talk to your car will shrink to something economically viable. And I moot that in future there will be 3 types of machines, and today we only have 2. We have CPUs for serial workloads. We have vector machines, mostly GPUs, for dense matrix workloads. And there will be something else. I've called it a graph machine. I expect the marketing people will think of a better name. And because efficiency favors heterogeneity, I expect we'll see all 3, and we'll see all 3 on the same chips. Finally, there will be a massive upheaval in software. Part of that upheaval has nothing to do with intelligence. It has to do with parallelism. C has been the language of the present and the future for 40 years, but unfortunately it has no native support for parallelism, and attempts to add parallelism to it have been very inefficient. Something else will come along. That's a big, bold statement for me, because I would never have said that at any point in my career to date, but now C is for the chop. The other key implication for products is this business that intelligent machines are doing probabilistic inference on probabilistic learned models. Like you and I, they will from time to time correctly compute the incorrect answer. They'll get stuff wrong. Your car will misidentify a pedestrian and run it over. This is unavoidable. This is information theory. I see AIG have offered insurance against cyber injury due to hacked IoT objects. This came out, yes, this week. They didn't talk about cyber injury due to incorrect inference, but it's in the same category. Of course, ultimately, they'll be better than us, these machines. So it'll be an economic trade, but they won't be fail-safe. They will, from time to time, go wrong. I haven't said much about connectivity, so I thought I'd just say a little bit. The point of the IoT is what? The point is to connect all those dumb sensors to something that can do something more intelligent with the information. No one wants to connect your toaster to your bicycle, do they? So we want to connect all the dumb stuff to cognitive service. That's the whole point of the IoT. I think the IoT connectivity side's a bit boring, actually. I think the intelligence side is what's interesting. And ultimately, that intelligence should be distributed, because distributed intelligence gives you responsivity, it gives you bandwidth efficiency, it gives you resilience to failure. And I do not, having spent 10 years of my life in a wireless company, believe in ubiquitous wireless service. You can minute that. So all moving machines, at least, will embed intelligence. They will not rely solely on the cloud. These are the 3 things I pointed to at the beginning. I think these collectively represent the biggest discontinuity in computing since Mr. Turing first sketched out the Turing machine. We've been building them ever since. And my personal take is that therefore represents the biggest technology business opportunity since the invention of the electronic computer, which is about 60 years ago. Thank you.